Computers, episode I-8, Combinatorial Logic. This is Imroy, and today we're going to talk about using the gates we learned last time, AND, OR, XOR, and NAND gates to create what is called combinatorial logic. Now, combinatorial logic is fairly simple. It's simply connecting the output of one gate into the input of another gate, and doing that over multiple gates so that you can actually end up creating some sort of circuit to solve some problem that you want. We'll start out with a simple one first. I'm going to create 4 inputs right here with one space between them. These are going to be our inputs, and I'll extend these out here. And the first thing we're going to do is let's create gates so that only if all of them are on does the actual circuit come on. So if this one and this one and this one and this one are on, then it's on. Now when we do logic gates, they are called from right to the left: A, B, C, and D. So in this case, the logic that we want to create is if A, B, and C, and D, then 1. So it kind of works like this. We write them out opposite, just like they were a number. So DCBA is the way you can generally do this. And then you say, all right, if it is 1, 1, 1, 1, our circuit is 1. Otherwise, 0. So that's how we're going to do this. All right, I'll get rid of these. And that's how that is. If A and B and C and D are all on, then we want a 1. So those are all AND. So we start by building AND gates. Very simple here. If you remember, an AND gate looks like this. It has torches on the top of these, there and there. We have one here. And then of course we put wire there. And finally here. I'm going to build 2 of these. Okay, here we go. And then lastly, I'm going to take a look at these and say, this should be on only when both these switches are on. On. You can see that it's off, and on, and it's on. So it's just our standard AND gate that we built last time. And of course the same will work over here when I turn these on. This one on. Now, the last part is we wanted these to come on only if all 4 is on, so we need yet another AND gate right here. So I'm going to put it out here, do this, bring this one this way, this one this way. And then of course I just built another AND gate because I'm going to combine those 2 into another AND situation. And finally, we'll bring this out here into a light. I forgot my torch here. So I actually built an AND gate. There's our light. Now I have AND. If A and B are on, and this one says if C and D are on, and then this one of course says if that condition is on and this condition is on, then we get a lamp. The way this is going to work is very simply turn any of these on. You'll see the light does not come on until I turn this one on. And there it is, it's on. Turn any of these off, pick any one, it doesn't matter. That light will go off. That is AND gates. Let's do the same thing right over here, but we're going to use OR gates. Do the same thing. I'm going to put down 4 inputs. And bring them out to here. And we're going to do ORs. So in this case, we're going to say if any of them, so this is going to be an OR situation. If A or B or C or D, then I want it on. Like this. That's going to be as soon as any single lever is on, we get it. So we write it similar to this. And the situation is, and this is a very simple logic. If any of these, we have this symbol right here, this is the OR symbol, C, B, or A, equals 1. We're going to do 2 OR gates, just like we did with the AND gates, here, here, here. And remember that ORs are very simple. They're just wired across the top. They're wired out to here. Now we'll just go ahead and connect these in. And the second part of this, as you can see it, is if either of these is on, this will come on. Very simple. So if either of those or both, it's on. So as soon as any switch is on, you get it. This will do the same thing, of course. We're also going to say here, if this one or this condition is met, so if A or B or C or D is on, so of course that's going to be another OR gate, just like this. And I'm sure you can connect them in the sides too if you want. I don't normally do this, but you can. I'll just show you this is possible to do. So we'll bring it out here. It goes into there, like so. You can do that with an OR gate or an AND gate as well. It all makes sense. And then finally, we'll put our light here, and we'll see what happens. Any single switch should turn this on. So as soon as any switch is on, the light stays on. Doesn't matter how many I have on, they can all be on. It doesn't matter. So that's an OR. So now we basically said if any switch is on, that is the root combination. But let's do one more. Let's say instead we want to say if this switch and this, or this switch and this switch is on. The last thing I want to do is take a look at these by saying, all right, 4 more inputs. We put them right here. There's line them up here. 1, 2, 3, and 4. And we are going to do our wiring here, just like we did before. Remember, we said if both of these are on, or both of these are on, we want the light to come on. Since it's an AND situation, if that one and that one is on, or this one and this one is on, very simple. I'm going to end up doing AND gates just like this. And then our last gates, as I said, if this condition is met, or that condition is met, this last one is going to be an OR gate, just like this. We'll elevate our light to make it easier to see. If I turn on any single switch, nothing will happen. If I turn on one of these switches and one of these switches, nothing will happen because our first condition is not met. I have to turn on 2 of these switches on either side. So if these 2 are on, you can see the light is now lit. Or these 2 are on, the light is lit again. So I turn any switch off over here, it's off. Now keep in mind it doesn't matter since we said that's an OR condition. They could all be on, and that's fine too. In this case, our statement here is if B and C, or B and A, then on. Keep in mind that we can also consider on as 1 or true, or powered or signal, however you want to think about it. If D or C, of course, if we wanted to make this very clear, I can do it like this. If D and C, with that OR symbol, or B and A, on, otherwise off. Okay, we'll work on truth tables later exactly what all this means, but we're just looking at how we actually combine gates to do various things. If A or B, the light comes on. If A and B, the light comes on. Or C and D, the light comes on. And of course, they could both be true as well. Another way to combine gates. Let's do something a little bit harder now. Let's say we want to do the same thing, but we want to say if, only if, we want to modify it and say if D or C, but not B and A, or B and A, but not D and C. So that means either this side has to be on, or this side has to be on. How are we going to do that? Well, remember we have a third type of gate that we talked about called an XOR gate that checks for exclusive. We said we're going to stick with the concept that both of these have to be on before anything occurs. So I'm going to have to build OR gates here as usual. These are AND gates. We build them like we always have. Build a lot of these, we'll get very used to it. Here we go. Wire here, here, there, and there. Now, if you'll remember when we wanted to do a different type of gate, and that gate was a gate that requires you to do one or the other, that was called an exclusive OR gate, meaning it is exclusive in OR condition. They both can't be set. So in this case, if I turn either of these on, you see our output turns on. In that case, we'd want our final output to be on. But in this case, if I turn this on too, get my wire complete here. And with them both on like this, we want to make sure that we don't actually create it. Okay? So do you remember how to build an XOR gate? It's fairly simple. We start with the AND gate. But you put an additional block here. The torch is just like the AND back there. So this is an AND gate that we just built. We're going to bring our inputs into it. Like so. We have our wire running like this. Of course, the last part of the gate is we bring the torches here and here. This completes the two NOT gates that we need. And then we run the wire from here forward into a block that inverts it once again, like so. And that then becomes our output, like this. So we'll elevate it. And put our lamp, which is our output here. Missed. There we go. Turn these off. And take a look. So here we have an AND gate with an AND gate over there. That is if that condition. If A and B, if C and D, those then run into the XOR gate. And the XOR gate has torches on top here. It has torches here as well. And the last piece that we need is we need to connect these across the top like so. Then this is an XOR gate starting from here to there. So now what this should do is, if I pick either side to turn on, such as B and A, the light comes on in that case. If I do any one of these, then it doesn't. Over here, same thing. C and D are on, the light will come on. Now the trick is, if I turn both of these on, the light should go off. Any one is fine because this condition is not met. As soon as I do this, the light goes out. So it's exclusively OR. I can't have all four, but I must have two, either C or D or A or B. So that's how this works. And that is how combinatorial logic works. In the next lesson, we're going to talk about how we can do more complicated situations, including some very more advanced, and we're going to talk about truth tables and how these all work together. be using the 4-bit bus over here to be able to take a look and do some actual and very interesting, which will turn out to be logic puzzles. Let me review real quickly what we did here today. Here is 2 AND gates going into a third. That is only if all 4 switches are. Here's 2 OR gates, or, which means if any of these switches are on, or multiple, then this light is on. Here we have if this is an AND gate, so if this and that is on. And then here we have if this and that is on. And then, of course, since we have an OR gate here, it's if these 2 are on, or these 2 are on, then the light is on. It doesn't matter how many on. Our last one here is only if this side or this side. Now, the last piece that I do want to show you is how you can build a very large AND gate. So let's take that first condition again we have where we wanted to say all 4 are on. I'm going to build it right here. Instead of using 2 AND gates, I'm going to build 1. And the way we do that is like this. You put a block in front of all of your inputs, like this, and then all the way across. Then we put torches on all the input blocks. It's back here. Then we bring a torch out anywhere we want. I could pick any of these. I'm going to put it right in the center. And then we wire all the way across the top of these. Now they're all wired together. Once again, I will elevate light up here. And then we just need to wire these in. So this will do the same thing that we did that first time with 3 AND gates. Only if all of these are on will our switch come on. And our finally, turning any one off, it goes off. This is actually how you do a multi. I could do as many inputs as I want. I could do 8. I also want to show you that, as I said, I can bring this torch out anywhere. Bring it out over here and wire it in this way. So it doesn't matter where I actually bring the output of this. Could I do multiple outputs? You can answer that simply by doing this. We'll put a light here. Yes, and sure enough, you can do multiple outputs, but that kind of defeats the purpose of what we're doing in combinatorial logic. So you'll notice in all of these situations we have a signal that starts in one and it propagates forward through the gates to an output that creates a condition that we're eventually concerned in. One single condition. This combinatorial logic because we move from the inputs straight through the circuits and the output. And there's only one path any of these can follow. So when I turn this on over here, these 2 are on, these 2 are on, and finally at the end, this is on or off, depending on our condition. So there's no wire. If I brought a wire out here, and maybe brought it later into the circuit over here or something like that, that is not combinatorial logic. That is something different, because combinatorial logic moves from the inputs straight through the outputs. That is it for I8. Tune in next time for our look at more complicated. We'll be looking at conditions that are both positive and negative, or zeros and ones, using our 4-bit bus over here. And that is where we'll pick up the next lesson. Give me subscribes and likes if you like what you see as we continue to build first our 8-bit CPU and eventually our 8-bit computer in Minecraft using Minecraft math and computers. Enjoy.